That the recording didn't start. All right, so now it has started. All right, so welcome everyone. Today the Splashdown session is focusing on optimizing the treatment of wetlands for total nitrogen removal. And for this session today, we are having Mireille Martens from Rietland and Otto Stein from the Montana State University, the Department of Civil Engineering. So today we will start with Mireille. Mireille will give us an overview of strategies for enhancing nitrogen removal in constructed wetlands and that are focusing on optimizing the denitrification processes and also implementing operational adjustments to achieve removal that has rates above 80%. And then we will continue with a presentation from Otto that will also give us an overview of the challenges that are associated with total nitrogen removal in wastewater treatment systems, and also a bit the approach on how they are working in the United States. And also we'll discuss a bit the nitrogen removal pathways for treating wetland treatments. So I think I will leave it to you both to give us an overview. So Mireille, we'll start with you. The floor is yours, so please feel free to share your screen too.
All right. Do you see is the screen visible?
Yes, we can see the right screen.
Okay. Okay, good afternoon, everybody. My name is Mireille Martens. I think most of you know me, and it's a pleasure to talk about improvements of wetlands and in this case, to improve the nitrogen removal. I'm not doing this alone, together with Otto Stein. And Otto has a presentation after mine, but we have bundled some numbers and some thoughts on the last slide I will present you again to have a vivid discussion at the end. Okay, so my presentation of around 15 minutes is, I'll give you a really short introduction. We will talk about scenarios that focus on the influent concentrations of CO2 and total nitrogen, which are coming into the system and how that impacts your denitrification. And I will show this with 3 examples. And after that, we go into solutions. So if what is in the influent isn't sufficient, what to do? What are the options then? And we have some examples on carbon dosing. Recycling is what recycling of the effluent. Otto will talk about that, and maybe to add an extra wetland. Okay, so the introduction. What is the problem in Europe, but all over the world, and also in the North America? There is we suffer from eutrophication caused by a lot of nutrients, nitrogen and phosphorus, and they cause in late summer algae blooms, and because of that the algae die, and then a lot of bacteria are breaking those algae down, and because of that they need oxygen, and that's why coastal dead zones are created, which is not good for the fish because they die because there's no oxygen, but they are also they cannot ammonia is toxic to fish, and it also decreases biodiversity because the species are eager to grow fast can dominate over the one who likes poor nutrient areas. Nitrogen is an interesting element in the biochemical cycle of nitrogen. You can see various forms of nitrogen. So depending on their environment, if it's in the atmosphere or in the marine ecosystem, they all have different forms, or the nitrogen has different forms. And the total we call the total nitrogen. But we in wastewater, we are most focusing on the removal of nitrogen. And if we talk about removal of nitrogen, we want it up in the air again in the majority of the cases. So first we do nitrification, which is ammonium or ammonia transferring into nitrate. And that's done in aerobic situations. So you oxidize nitrogen. And then in the denitrification, you don't want any oxygen in your environment, so you need anaerobic situations where the nitrate is transferred in nitrogen gas. So nitrogen is reduced, but you need a carbon source. And this is actually, in the most of the cases, the Achilles heel of the system. So what you need to remove nitrogen, so to get nitrogen back into the air, so to have denitrification, is the carbon. Let's go to this once again. So what we do most of the time with Rietland, we have an aerated system, or we always start with a vertical system. Actually, the picture on the right side is a horizontal flow, but just to give you an idea. So the first part of the wetland, we want aerobic conditions because we want to remove carbon, so the BOD, COD should go down. So that's why you need the oxygen, and also you want to enhance the nitrification. In the second part, we focus more on denitrification, so low in oxygen, and you need carbon for that. But as I explained already, the carbon is removed in the first part already. So depending how much carbon is coming into your system in the influent, you still have enough left over at the end to do denitrification. But in a lot of cases, that's not true. So if we analyze this, so if you have in your influent water matrix, for example, COD to nitrogen ratio of over 20, then you could have 90% of total nitrogen removal, which is excellent. So to give you an example, that are dairy farms and could be in a laundry. I'll explain more into depth later. A second part is again a COD ratio to total nitrogen is a little bit more than 4. You can have 70% of nitrogen removal. We take into account domestic wastewater. If you split it up into gray domestic wastewater and black, in gray there is not so much nitrogen to be found because that's most in the urine. But so the low, you have a low nitrogen concentration, and there is sufficient amount of carbon to do the denitrification because there's not so much in it. In the black domestic wastewater, there's a high concentration of nitrogen, and in a lot of cases, the carbon is limited. Well, it's abundant present, but to have sufficient amount to be able to denitrify the high nitrogen concentration, not so always so doable. And then you have the COD concentrations, which are around 1 or even the ratio COD-N around 1 or even less. Yeah, and then we have 60, but way less percentage of nitrogen removal as well. And I'll give you an example of that on the Orchid farm. Okay, so example number 1, which is Wasserij Tony. It's a laundry company. It's important to explain that this laundry company only treats table clothes and bed sheets, so no synthetic materials. So if we start at the right side, you can see a table with influent data. And we are most interested in the COD and the total nitrogen. You can see there's a big difference between COD and total, and that's also plotted in the graph below. So if we look at the COD-N ratio at the left side, you can see there's a 70 to 1 ratio. So you could expect that it's sufficient amount of carbon present to denitrify. So we have built a wetland over there at the laundry, and actually there were the biggest issues were the cotton lint and the detergent, but they were all biodegradable. So currently, because this is functioning from November on last year, there have been no problems at all. So the area of the wetland is 350 square meters. And if we look at the influent and effluent concentrations and the removal data, you can see that, well, everything is removed nicely. So the COD has a removal percentage of 98%, and the total nitrogen is 94%. So that's we are very happy with that. But this is actually no surprise because the COD N ratio is very high. And the specific load of nitrogen is also 2.4 grams nitrogen per square meters per day. So that's not so overloaded. So this is quite ideal situation. If we move on to example number 2, that is the multi-source campsite. Probably you have heard about it. And here we have split up the domestic wastewater in the grey water and black water. Let's start with the grey water. So the setup is again the same. Let's have a look at the table. If we look at the COD total nitrogen, well, you can see it has a COD N ratio of 5.7 to 1, more or less, which is, you would assume this fairly enough to do some nitrification. You can also see that on the graph on the right side. And if we look to the black water, then you can see that actually the COD is only a little bit more present than the total nitrogen. So actually this ratio is not so interesting. It's only 1.4 to 1, and which is also very visual in the charts at the right side. So you would assume that the gray water, the denitrification there would be higher than the black water. It's also good to have a look at the BOD. So that is a lot of available carbon for the microorganism. That's also quite high for the black water. It's almost 400 milligrams, so which is also good to know. So what have we designed for the multi-source project for the campsite? So we have an area for the gray water of 44 square meters and for the black of 32 square meters. But the specific load, we have designed it for 8 grams nitrogen per square meter per day for the gray water. But for the black water, it's way higher. It's 44 grams nitrogen per square meter per day. But this is how we designed it. Also, we have calculated how much water they use, but apparently the use of water is quite different than we thought it would be. But these are the design parameters we used. If we check for the removal efficiencies for the gray water, then we have a removal, 71%. Actually, I was assuming that would be higher. Actually, we're not so happy with the COD removal because that's only 83%, and then the majority of the cases we have more, always over 90. So the BOD is removed nicely, is 99%, but the COD is only 83%. And the specific load is we have designed it for 8 grams nitrogen per square meter per day, but because of the different the camping guests are not behaving like we thought they would behave, so that's why in reality the maximum load is only this. and we have expected it to be 8. If you look at the black water, the influent and effluent, and we look at the table again, then you can see that the removal of a COD is much better, is 95% compared to the 83 of grey water, and the total nitrogen is 72%. And this is actually a surprise, because if we look at the COD N ratio, which is 1.4, you would assume that it would be worse. Definitely, if you take into account that the specific load at this location is more than 50 grams. Well, that's the maximum of nitrogen per square meters per day. So this is a campsite which is open over a large period of time, and sometimes you have peaks during summer breaks or long weekends, and then it really goes up and down. So, but this number, this 50 grams of nitrogen per square meter per day, is a specific load of an intense period. And then I have another example, which gives you some insight in extra solutions. So if you want to improve your nitrification, and it's you cannot do anything with the influent water because there's not sufficient carbon there. There are 3 options you can do. You can add an extra wetland, you can add a carbon solution, or you can recycle your effluent. So I'll explain the Orchid farm in Belgium, which is doing the first 2 solutions, and then Otto will explain the recycling of the effluent. Plus, Otto also has extra information on the horizontal subsurface flow wetland and the denitrification occurring there. So example number 3, the Orchid farm. This is the data we have received from the Orchid farm. So they have again a COD-TN ratio. But if we look at the ratio, it's the other way around. There is much more total nitrogen than there is COD present. So nitrification needs carbon, so that will never happen if you don't do something extra. So the COD-N ratio is 1/2 to 1, and the specific load is 2.9 grams nitrogen per square meters per day in this. If we check the, well, I'll explain later. Okay, what is this pictures? If we start at below drawing, you can see a lot of different numbers. So all the water is buffered. The wastewater of the Orchid farm is buffered in number 1, and then it leads to number 2. Number 2 is an aerated vertical constructed wetland, a vertical subsurface flow of 20 square meters. So number 2 in the top picture is then the vertical wetland, the vertical aerated flow. After that, the water flows into in series in 3 basins, in 3 wetlands, the free water surface. And the first one is 250 square meters, and then the 2 later on are 125 square meters. So you can also see the pictures with the 3 on it. They are like the free water surface. And we played a little bit around with the water level in these 3 wetlands. So we have improved the biodiversity because of that. Then the water flows from number 3 and number 4. Number 4 is actually a tank with a pump. So it's a pumping area, but that is the location where we add the carbon source. So if the carbon source is mingled in the basin, in the tank, then it's pumped to number 5. And number 5 is again an aerated wetland, first a vertical flow and then a horizontal flow. It's aerated, but not that much, because we want to have denitrification. But if there's excess of carbon, which is not used for the denitrification. We want to aerate it, or we want to degrade it, so it's not coming in the ditch afterwards. And then it goes into number 7. The water flows in number 7, and number 7 are tanks with an adsorption material to trap this phosphor. Okay, some more information. It took us a long time to get, well, we're still trying to operate this in a very good way. If we look at the chart on the top, you can see the green horizontal line is the threshold, should be 50 milligrams per liter of total nitrogen. And the majority of the time we're over, but we're getting there. So what you can see is like the green star, the first period that it was below the threshold was during summertime. And actually the idea is that there's no carbon added at the moment when the temperature is high enough, because then there's sufficient organic matter which comes from the plants in these different wetlands, definitely in the free water surface. And in wintertime, you can see that the bacteria, they need more time because it's a little bit cooler. So to compensate for that, we use the carbon source. And that is visual in the other chart, a little bit lower. So you can see it says SF, so the free water surface. So the first pond, the second pond, and the third pond, you can see that the removal of nitrogen is not that high. But then if it comes with the carbon source in the forced bed aeration, so FBA, number 2, so in the aerated wetland, but then it contains the carbon, then there's a lot of removal in wintertime. And then the last part in the is the adsorption tank. But we had some difficulties. That's why the line of the above chart goes a little bit up and down. We had some troubles of mixing the carbon source in the tank because it was floating on the surface. So before we had a solution to that, it took some time. And then the moment the pump went on to get the new water with the carbon into the aerated wetland, in that case, the blower was also on, but that means that you immediately degrade your carbon. So now we changed that the aeration starts after 20 minutes after the carbon is added to the system, so that you first focus on denitrification and afterwards create aerobic conditions. And then, yeah, sometimes things go wrong. We have a temperature sensor that gives a indication to the PLC when carbon should be added or not. But a rat was walking around and disabled the temperature sensor. So that also was a setback. Okay, so what results do we have? Well, we're not there yet, and actually these are average numbers, and as you have seen of the previous graph, when the values went up and down, this is not a clear overview. But so we're not there yet, that's certain. We are the COD removal is not good, is way too low, and the nitrogen level we have to meet the threshold of 15, and we're not there yet as well. But we are getting there. In a few months' time, Flor from the University of Ghent will present this with far more data on the Congress in Martinique. And now we're heading for the United States. Should stop sharing.
Thanks a lot, Mireille. In case there are any questions, we will take them all together with a discussion after Otto's presentation. So Otto, over to you. You can also share your screen.
Thank you. Thank you, Mireille. Let me get my screen shared here. Gotta find the right window. Here we go. Should work. Here we go. Can we see that well?
I think it's still loading. Yes, now we can see it. So please go ahead.
Okay. All right. Well, so first off, I have to admit that if you were at the Wetpol conference in Bruges, you may have seen this before, but I wanted to talk about what we have done at the Bridger system and to try to increase denitrification and total nitrogen removal. So we have two systems at the Bridger Bowl ski resort, which is just outside Bozeman here. We have the pilot wetland, which was planted in 2013. We had a design flow of 4 cubic meters a day with a surface area of 95 square meters. The data that we got from that over the first few years was good enough that we went ahead and designed the full-scale wetland system, which was planted in 2019 with a design flow of 40 square meters per day, and everything worked so well, you can see that we got 10 times the flow, but only 5 times the surface area, essentially, and that is proven to work very well as well. So one of the nice things about the Bridger Bowl system is that the Bridger Bowl has allowed us to keep the pilot system running. And we can use that for research purposes. Essentially, the water comes from that system and into the full-scale system, so we can do whatever we want with it. We can break it. We can play with things and figure out how to optimize things, essentially. And so the pilot remains part of one of the pilots then in the MULTISOURCE project. So some of the things that are unique about this, we're relatively high elevation. The ski resort is really only used in the winter. There's no lodging or anything there. It's sort of a day use ski resort. So in the winter, then our water temperature is about 3 degrees C, and because there is nobody living there, it's only toilets and kitchen waste. So we have pretty high COD concentrations and pretty high total nitrogen concentrations coming in. So the basic schematic of what we decided to do up there is that water is clarified in sedimentation tanks or septic tanks. That water then goes into a first stage where we have partially saturated conditions. So the idea here is that we're going to get COD removal in both the aerobic upper layer and in the anoxic lower layer for denitrification. So we'd have carbon there. Presumably then we'd remove almost all of the COD, and then that effluent would then from the first stage would go into the second stage where we would have nitrification. Water comes out of that second stage, and we can either discharge that water or recycle that water back to mix with the first stage there. So each stage happens to be divided into 2 identical cells. And again, that was for research purposes. So we could load one side differently than the other and have the exact same influent coming into that. So what can we do to try to play around to try to increase carbon, COD, and total nitrogen removal? Well, we have the ability to adjust the hydraulic loading rate because we have a backup system behind us. So essentially, we could keep loading it until it doesn't work anymore and figure out what that value is. Of course, we can't control mass loading and hydraulic loading independently. We can put more on of everything or less on of everything. We could change the saturation level in that first stage, so we could make it almost completely saturated or almost unsaturated. We could vary that circulation ratio, how much of that recycled water do we come back and mix with the raw influent coming in. And then we could play with how we dose it and what's the frequency and the dose volumes once we have an overall hydraulic loading rate. So do we do lots of little doses or a few big doses, essentially? So just to give you an idea of what our overall performance has been up until this last season, essentially, loading rates that we've done, this is to the pilot system. You can see those. We've done, 3 different recycle ratios. We've had hydraulic loading rates of somewhere between 5 and 60 centimeters a day. We've done different dose frequencies for between 3 and 12 doses per day. Recycled dose frequencies then of somewhere between 4 and 36. And we've looked at specifically then at 2 different saturation levels of the wetland. So this is blind to all the different things that we have done over the years with that. So this is a mix of all of those different options that we've looked at. But I think the point being here is that overall we get very good removal of almost everything. We get 96% removal of COD and 69% of total nitrogen. And equally important for us is that we convert almost all of the incoming reduced nitrogen, which is almost exclusively ammonia. When it comes out, it's almost all nitrate, and we're still getting 60% removal. So certainly suggests we're getting both nitrification and denitrification if we just look at what comes in and what comes out. So essentially what we had done out of all of those options, what did we decide was the best way to run it? We had a COD loading rate, as long as we keep it under 120 grams per square meter per day. We removed most of the COD in that first stage. Turns out, and not surprising, that if we have a larger saturation depth, we get more denitrification. So we went with the larger depth. We did not want to go deeper than that because we can have extremely cold temperatures, -30, and we did not want to freeze the surface. So we try to keep an unsaturated zone at the top. We looked at the best recirculation ratio seemed to be about 2 to 1, recycle then to the loading septic coming into it. And we did dosing schedules. What we found was that smaller frequent doses seemed to be better. You could see some of the results in this and some previous work that we've published. Again, this is all from the pilot system. But one of the things that was very clear is that even when we've sort of optimized these other things, we could probably get better TN removal if we could somehow figure out how to get more carbon down into that saturated zone at the bottom, and that we're carbon limited in the denitrification zone. So essentially the question then becomes, how can we get more COD down into that zone so we can increase that COD-N ratio that Mireille was talking about? So again, we've got this saturated bottom and this unsaturated top. The goal here is essentially the raw water coming in is both high in COD and ammonia. And then the recycle brings in all of this nitrate. And so some of the COD will end up being removed in this aerobic zone, but we would like most of it to get down into that saturated zone where it could mix with the nitrate and we can get denitrification. So again, denitrification in that saturated zone. Then the ammonia would come out and go to the second stage where it would be turned into nitrate and then completing the loop and coming back as nitrate. So how do we get more in there? Well, we could always just increase the COD loading rate. That's one option. We could raise the saturation level. We could decrease the recycle ratio. But if we pick all of these the same, and we said we've already optimized these, then could we somehow increase that ratio in the saturated zone by putting very large septic doses into that? And the logic behind that was that as this water travels through the unsaturated zone, some of it is going to stick on the rocks, and so this idea of specific retention, the volume of water that would be retained once it's gravity drained, that water that sits in there then could, the COD that's in that water could be removed, and then we lose that COD before it can get down into the bottom. So if we put a big dose volume, almost all of it would gravity drain right through, and only a small fraction of that would remain. So presumably a large dose would then put more COD into the bottom. So that was the basic premise. In the one season we were experimenting with this, essentially, we had two different level. Our septic loading rate was right around at our design loading rate at about 4 cubic meters per day. We're saturated at 80%, recycle ratio 2 to 1. At this year, we did not have the ability to change what happened to the two reproducible cells in there, so they were both dosed exactly the same. Essentially, we had 18 recycled doses of 0.8 centimeters. The first half of the season, then we had relatively small septic doses and more of them. In the second half of the season, we had a much larger septic dose. So the only thing that was different was the size of the septic dose that we put onto the system. Everything else was the same. So in the second ski season, we had put a new valve in so that we could actually load them differently. That was something that we wanted to do for years and managed to finally make it happen. Loading level was a little bit higher, about 50% higher, but the saturation level and the recycle ratio were the same. So now we could dose things independently. So one cell was again dosed with a few big doses, and the other cell was loaded with with a lot more smaller doses. So even more extreme than we had before the first year. So yeah, you can see 12 septic doses of 1 centimeter versus 3 septic doses of 4 centimeters. Again, the overall loading rates are the same. So here's a lot of data in a table. Let's just focus on a few key things. Influent was similar to what we've seen before, but actually a little bit higher in general, both for COD and ammonia. And we tended to get very similar removals. In fact, even slightly higher than what we had seen before. So our COD to nitrate levels are very, very similar, about 4.8 or so. So a little bit under 5, but approximately 5 or so in this case. So again, the removal of TN was, above 70%, approaching 80% in the one season. So if we try to peel the onion layer back a little bit more and look a little bit more closely at this, we had, again, small doses and large doses of septic volumes. That's the big difference between these things in here. And what we can see is that when we had large doses, then this is a loading of nitrate to those first stage and how much of the nitrate was removed. So of course, if we get closer to the 45-degree line, the better off we are. And so we saw large doses tended to plot closer to that 45 line than small doses. So sure enough, it did appear that larger doses tended to improve performance for total nitrogen removal then. The changes are pretty subtle with the low loading, but if you look at the higher loading, which we did in the second season, then we had a much bigger difference between dose volumes in there. So we could have just stopped there, but we started thinking about this more and we go, well, is it really the dose volume that's controlling this? So here's the same graph on the left side, and on the right side, then we are adding the COD loading to the cells. And if you remember, we had a higher loading rate in the second season. And so now we can see for COD loading, larger doses, we had differences between what happened in one season versus the other. And the small doses plotted like this. Key here, though, is that in that first season, we had a temporal variation. Loading rate goes up as the season goes on, as more skiers come in to visit. So we had a temporal variation, which we did not have when we had the second season then. So again, I think what I just said, COD loading increases throughout the season. We had high dose volumes later in the season in the first year. In the second year, then we had small doses were more efficient in removing the COD. And again, that would make sense because small doses, maybe we remove more COD in that aerobic zone at the top then. So it might just have been that we had more COD available and it had nothing to do with dose volumes. And that was a question that we wanted to try to answer. So maybe it's that the smaller doses enhance COD removal and not denitrification. So again, we also have ammonia that was coming into this, and it turns out that we did remove some ammonia in that first stage. Presumably that's because we had nitrification in the upper zone associated with that. And so this was highly variable, as you can see here, but sometimes it appeared that we lost 50% of the ammonia in that first stage, and we thought that most of the ammonia would go right through. So especially with smaller doses, we got more ammonia removal, presumably because more water was sticking being held in that upper layer. So what is happening with that? Well, we don't know because we couldn't measure things, but this was our premise. The COD would be removed in both the aerobic and the anaerobic zone. We'd have the nitrate coming in. But it might be if we convert a lot of ammonia to nitrate, then our loading to that saturated zone is not just what's coming in from the recycle tank, it's the amount of ammonia that was nitrified in that upper zone. So our COD to N ratio may not be as good as we thought it was because we actually were loading more nitrate into that lower zone. So we tried to look at this again in the aerobic zone, then presumably that would increase COD removal, it would increase nitrification. Assume that has no effect on the nitrate, so the anoxic zone there can only receive what comes through. So we get more nitrate, less COD, and poorer nitrification if I had small doses of water coming in. So it's a double whammy, if you will, more nitrate and less COD. But it's really hard to quantify that because all we can measure is what comes in the top and what comes out the bottom, right? So we don't know what the split would be between the unsaturated and the saturated zone. But we could try to model this with a really simple model. So what we did was say, well, the amount of nitrate we created and we assumed that was in the aerobic zone was the ammonia in and the ammonia out. Then the amount of nitrate removed was what came in with the recycle and versus what came out, plus what was created in that upper zone. We could estimate how much nitrate was removed by doing some stoichiometry and say that the COD removed by denitrification is 80% of the nitrate removed. And then we could make an estimate of the aerobic COD removed by what came in and what came out, minus how much was done by denitrification. So we've ignored a lot of other processes, but we focused on that. And so here was our original raw data, what came in and what came out. This was in that first year with small doses. If we considered how much was created, you can see, for one thing, that starts to make more sense. We get a very obvious more loading in, more removal, and we see a very both still distinct difference, but also something that makes more sense, a more linearized version of what came in. So that seems to make sense that that's what happened. And we get this relatively linear response with small doses being poorer than large doses. If we look at the second season as well, then when we consider how much was created, the data is a little bit noisier, but we definitely get a little bit more linear with the large dose. And we see more removal with the small dose, but removal went up. But maybe we're just kind of hitting a maximum load there of how much could come in because we're just out of COD at that point, no matter what happens. So what was the conclusion from what we got from this particular study then? Overall, we had great performance. Certainly the dose volume does influence performance. So even with the same loading rate, with the same influence COD to N ratio, how we dose the system seems to have an influence on denitrification and TN removal. I do want to point out that, everything that we just showed here for dose volume was for a specific loading rate, for a specific recycle ratio, for everything else the same. If we change some of these other parameters, different dose volumes might have different optimalities between it. I mean, there's interactions between all these terms. So I want to thank Bridger Bowl for letting us play with our system to give us a toy. It's been really useful for MULTISOURCE and for us and for just figuring out how to better optimize vertical flow wetland systems. And so with that, I guess hopefully we've left some time for some questions.
Well, thank you very much, Mireille and Otto, for these presentations. And I think, Mireille, you also have one slide, right? That we could potentially have for the discussion, or no, some comparative.
Yes. This was Otto. So we talked about denitrification, and if there's sufficient amount of COD and TN in your influent, then you have a large COD-N ratio, and then you have good results. So that was one of the examples. So the 70 has a better result than the half. And then we talked about loading as well, but it doesn't say it all. As I said, it's not clear why the gray water has not such a good denitrification, because probably the carbon is not so available, but it's not so clear, but because the BOD was quite okay. And also we thought maybe the environment is not anaerobic enough, but then again, the COD removal was only 83%. So you would assume that if the aerobic conditions were very high, that the COD also was very high. And also for the black is the opposite. We didn't thought it would have such a good results, but it has. So this is like an overall table of all the different examples we showed. And at the end, you can see Otto's. So maybe this is like a nice overview to have a discussion, or maybe have some questions. And I'll put it not in presenter mode because I cannot see anybody then.
Yes, I think we see it anyways fine. So I think Fabio had already written a question on the chat. I don't know, Fabio, if you want to just go ahead with your question.
Yeah, it was for Mireille, and it was just about the possibility of making reuse of the effluent of the black water treatment, which is very rich in nitrates for the numbers I've seen. I mean, the ammonia is very low, so those are all nitrates. And therefore, I would asking if it is possible to make reuse of that effluent as an irrigation solution. But Mireille just replied, so Mireille, you can go on.
Yeah, I replied that. Well, people are in Blackwater. There's a lot of pathogens, and people don't want. Definitely on a campsite, they don't want to have the risk that guests could be become sick or whatever.
Not even adding a very nice UV lamp, for instance, for killing all the possible pathogens.
Yeah, we had a lamp, but that was installed for the grey water. So the grey water was recycled for the toilet flushing, and so after the grey water, because in campsites people pee in the shower, so that's good to have even a UV lamp on the grey water. And then, but then that. We made a calculation, and actually from all the equipment present there, the pumps, the blowers, and the UV light, the UV is the most costly because it should be on 24/7. So because of that, the owner switched it off more off than it was on, which should not be the case. So because all of these things, yeah, that's the thing that happens in real life. So that's why it didn't go ahead with the UV light. But anyway, the black water was never intended to be reused.
I think I'll hear. Thanks a lot, Mireille. We still have some minutes, so I think we can go ahead with a couple of questions. So please feel free to raise your hand if you have any questions either for Mireille or Otto. Right? No questions.
I can
So,
have one, but it's still me.
Well, then please go ahead.
So one
Fabio.
for Otto, which is how, so in real life management of the system. I mean, here you are controlling almost everything. So having a higher variation of the loadings, the fluxes, and so on, how could we try to determine, maybe by some smart sensoring, the best number of septic loads to the system in order to get the higher performances?
Yeah,
If you have ideas about that.
Well, we've been trying to characterize this a lot more. I think, the media size is going to determine what that specific retention volume is going to be of that media. So we have actually been looking at both the new pilot system that we've built at our Bozeman wastewater treatment plant and also in the lab, trying to characterize the dose volumes relative to the specific retention of that particular media. And if you think about it, if your dose volume was exactly equal to your specific retention and water didn't, and there was no mixing in the system, that would be the optimal dose volume to be equal to exactly to the specific retention. And if you put more than the specific retention of the system in, then most of that, anything that's bigger than a value of 1 is going to go right through. But there's also a lot of mixing that goes on there. So 1 is a theoretical best, but it's always going to have to be lower than that. And so we're in the middle of some experiments right now where we're looking at 0.3 and 0.17, and we're going to look at 0.5 here in a minute for one hydraulic loading rate, and then look at a different overall hydraulic loading rate and repeat that again. And so far, it looks like the 0.3 is the lower the dose volume, the better, the more we retain within that system. So, like if I just wanted to rain COD through, I would just put a dose volume that's 3 or 4 times the specific retention, and it would go right through, right? But if I want to retain things in there, then I want to go lower than that. So in this case, we're looking at trying to maximize nitrification. So in this case, we'd want to, for what we're doing right now, so we want low ratios. To rain it through, you want bigger ones, right? And the other thing I'd say is that we have a vertical flow system, but if I didn't have to worry about freezing, I wouldn't have any aerobic zone in the first stage at all. I would saturate that virtually to the surface, and with a low COD ratio. And as my COD ratio goes up, maybe I want a little bit more aerobic activity to begin with to remove some of the COD. So a million things to play with, but the higher the COD to TN in the influent, the more aerobic I want that first stage to be, and the lower it is, the less aerobic I'd want it to be, essentially, is the way I see it.
Thanks. I don't know, Mireille, if you want to add something here.
No, well, I want to add a question. Is that okay?
Yes, please. Feel free. I hope you both have the answer though to these questions.
Do you still see the screen or not? I have no clue.
Yes, we can.
Yes.
Yeah, okay. Actually, this is, I cannot explain why the gray water has the same removal efficiency as the black water, because the gray water has a much lower TN loading, but also has a much lower and a higher COD N ratio. So you would assume that would perform better. So we thought, okay, maybe the carbon is not available. So because it needs carbon, and that is the COD was lower. But then in the COD, half of it was BOD. So I still not can figure it out why we have a removal of only 71% and it's not higher. And it's not because it's not anaerobic enough, because otherwise the COD removal would be better. In aerobic conditions, you could assume that the COD would be more than 90%. So I cannot figure out why the gray water.
Mireille, is there a difference in the type of nitrogen that's coming in between the gray water and the black water? Is one more exclusively ammonia or TKN, or is there some nitrate in the gray water coming in, or is it all ammonia too?
Gray. No, this doesn't help. This is gray water. This is ammonia. No, ammonia is low, 5 milligrams per liter.
Yeah, so what we don't know is if your TN is already, if it's already nitrate, then that might be making a difference in there, right? You don't have to worry about having oxygen for nitrification then in that case. But I don't know, when you only, I mean, for us, we've done enough TKN to NH4 for the Bridger system to know that by the time it comes through the septic tanks, there's really not any organic N left. But what I can't see from looking at your table there is the difference between TN and ammonia. Organic N that has to still get to ammonia, or is it nitrate that's already gone through that stage?
Yeah.
So that would be a question to ask, to maybe take a measurement of maybe.
Yeah. Thank you. More questions. Good.
I mean, that's maybe a difference.
Thank you, Otto.
I don't know if someone else would like to answer Mireille's question or have any experience with that. Or if not, I think that maybe this is something that you could like look into future projects potentially. So if there are no more questions, and I think we are right on time, then I would like to thank again Mireille and Otto for their presentations. I think it was very informative because everyone was here listening throughout both your presentations. So I would like to thank you very much. And we will see then each other to the next Splashdown session. So thanks a lot and have a nice afternoon. Otto, have a good day ahead.
Thank you. See everybody. Yeah.
Bye-bye.
Bye-bye.
Hope to see you in
Thank you very
Martinique,
much.
if not before. Yeah.
Ciao.